Hello. In this lecture, we'll be studying about boost converter, which is a step-up converter. That is, it increases the output voltage more than the input voltage. Now, boost converter is a converter which makes the output voltage output greater than voltage input. That is, in this case, no matter what input we provide, the output voltage will be greater. Now this is the circuit of boost converter. We'll see that there is a change in the position of inductor, diodes and the switch as compared to buck converter. So just like the buck converter, we'll again consider the on state and off state for our calculation. At on state, the switch is on. If this is short circuited, current cannot flow through this direction, as this is the minimum impedance path. As a result, the loop of current is this. Now we are considering this as V input and this as VL, or inductor voltage. So when the switch is on, we get minus VI plus VL is equal to 0, or we find VL is equal to VI. This is equation number 1. Now when the switch is off, since this is open circuited, no current can flow through this. As a result, this is the direction of flow of current. Again, we are considering this as VI, like the other case, this as VL, and in this case the output voltage is V out, V naught. Now here, by applying KVL, we find minus VI plus VL plus VO is equal to 0. From this we can write VL is equal to VI minus V naught. This is equation 2. So when the switch is on, VL is equal to VI, and when the switch is off, VL is equal to VI minus V naught. Now for a complete cycle, we know that 0 to t integration of VL dt is equal to 0. Now we can divide this into two parts. Firstly, the on part, that is 0 to t on. When the switch is on, VL is equal to VI from equation 1, plus the off part, t on to t. Then VL is equal to VI minus V naught. We get this from equation 2, and the total summation is equal to 0. From that we know that VI and V naught are both constant, so we and not dependent on time, so we can get those out of the equation. So VI integration of dt 0 to t on plus VI minus V naught integration of t on to t dt is equal to 0. From this we can find VI t on minus t plus VI minus V naught t minus t on is equal to 0. Sorry, here not t on minus t, it would be t on minus 0. Okay, so we get this equation. We can modify this equation, we can multiply these and get VIT on plus VIT minus VIT on minus V output T plus V output T on is equal to 0. From this we can see that this V input T on gets cancelled and what we can find is VIT is equal to V naught T minus T on. That is, V output is equal to V input into T divided by T minus T on. If we modify it, what happens? VI T by T, we are dividing both the numerator and denominator by T minus T on by T. So we can get Vi 1 by 1 minus T on by T is equal to D. So 1 minus D. So we get the relations V output is equal to 1 by 1 minus D into V input. This is the voltage relation in case of a boost converter. Now it is to be noted that D is always less than 1. If D is less than 1, 1 minus D has to be less than 1. If this is less than 1, 1 by 1 minus D has to be greater than 1. As a result, our output has to be greater than input. That is, V output has to be greater than V input, which is true for boost converter. Now let us look at the current relations. For current relations, when the state is on, we have already obtained VL is equal to VI. So IL, when the state is on, IL will be 1 by L integration of Vi dt, that is Vi by L T, Vi by L T. That is, the IL will be a straight line of positive slope. So here we can see when the switch is on, the IL is a straight line with positive slope. When the switch is off, we get VL is equal to Vi minus V naught. So IL is equal to 1 by L integration of Vi minus V naught dt, that is 1 Vi minus V naught by L t. Now it is to be noted that in case of boost converter, V output is greater than V input. As a result, since V output is greater than V input, what do we get? We get this as a negative value. So the slope of this straight line will be negative. As a result, the current will decrease. So while designing a boost converter, we have to note that we have to make sure it maintains in a continuous conduction mode. That is, the current through the inductor never gets 0 or below 0. Okay, now input output relations of current we can find out. In case of on state we get I in is equal to IL and I out is equal to 0. In case of off state also we get I in is equal to IL and I out is here IL. As a result, we can get in both on and off state I in is equal to IL and I out is equal to IL only in the off state. That is, only in this only in the fraction t minus t on divided by t. Only in this fraction of time I output is equal to IL. Now if we find out input output relations, I out by IL, I in is equal to IL t minus t on by t by IL are cancelled. Here we get 1 minus t on by t. This is equal to our duty cycle D. So we get I output is equal to I input into 1 minus t. It is to be noted that since t is less than 1, 1 minus t is less than 1. So I output is less than I input. In case of boost converter, V output is greater than V input, but we get I output is less than I input. And this is the input output current relation. That's all for this lecture. In the next lecture, we'll be studying about the buck boost converter. Thank you so much.